So we are very happy today to have Sejun Park from the Korea Advanced Institute of Science and Technology tell us about recent progress in understanding the expressive power of narrow networks.
I'm Sejun Park, and I'm gonna introduce my work on expressive power of narrow networks. And this is a joint work with Jeori, Yoon, and Jinwoo Shin. For designing network architectures, determining width, depth, and number of parameters is critical. And definitely larger networks are more expressive, but they require more computational power and memory. Therefore, characterizing the minimum size, such as the minimum width, the minimum depth, and the minimum number of parameters for representing a target function is important. The classical results on characterizing the minimum size of networks focused on shallow and wide networks, which have bounded depth and arbitrary number of neurons in hidden layers. For example, the classical universal approximation theorem shows that the minimum depth required for approximating arbitrary continuous function on a compact domain is exactly 2. And this result naturally indicates that two-layer networks can memorize any finite set of input-label pairs. So for memorizing finite input-label pairs, people studied how many parameters are required, and they show that data and parameters are sufficient for memorizing arbitrary and input-label pairs. However, these results cannot be applied to recent deep architectures. So in this talk, I will investigate the deep and narrow networks using ReLU activation functions, which have bounded width and arbitrary number of hidden layers. And specifically, I will consider two problems. In the first part of this talk, I will talk about the universal approximation with bounded width. It has been discovered that there exists some critical width that the network of this width are universal approximators, but networks narrower than this width are not. However, the exact value of this critical width was not known. So in this talk, I will introduce our exact characterization of this critical width, which is the minimum width enabling the universal approximation. In the second part of this talk, I will investigate how many parameters are required for memorizing arbitrary and input-label pairs. And while all existing results requires data and parameters, I will introduce our result on memorization using a number of parameters sublinear to n. Now I will introduce our result on the minimum width for the universal approximation. First, let me introduce the formal definition of the universal approximation. We say networks are universal approximators for some function class endowed with some norm if for any target function in this function class and for any error bound epsilon, there exists a neural network approximating the target function in epsilon error. And the minimum width required for the universal approximation has been mostly studied for two function classes. The first one is the LP function class, consisting of functions from the dx dimensional space to the dy dimensional space, having finite LP norms. And this class is endowed with the LP norms, defined as the integrated value of a function. The second one is a class consisting of continuous functions from the dx dimensional unit cube to the dy dimensional space. And this class is endowed with the uniform norm defined as the supremum of function values. And here, the best known lower bound on the minimum width is dx plus 1 for both function classes. And the best known upper bound is at least dx plus dy. And so the gap between the best known upper bound and the best known lower bound is at least dy. And in our work, we closed this gap and obtained the exact minimum width. And first, we proved that the minimum width for approximating LP functions is the maximum over dx plus 1 and dy. And we checked whether the same minimum width holds for approximating continuous functions in the uniform norm, but we found that it does not. In particular, we proved that the minimum width for approximating continuous function in the uniform norm is strictly greater than maximum over dx plus 1 and dy when dx is 1 and dy is 2. And these results indicate that the minimum width required for the universal approximation depends on the target function class. And we further checked if we can reduce the minimum width for approximating continuous functions using other activation functions. And we found that using additional indicator function reduces the minimum width to the maximum over dx plus 1 and dy again. And this result implies that the minimum width depends on the type of activation functions. And in the next slide, I will briefly introduce the proof idea for the network construction achieving the tight minimum width maximum over dx plus 1 and dy. Okay, so first consider approximating some target function f star from the dx dimensional unit cube to the dy dimensional space. And we approximate this target function using some encoder and decoder. Here, the encoder maps an input vector to some scalar value, and the decoder maps the scalar value to some vector close to the original input vector. And therefore, concatenating the encoder and the decoder approximates the identity mapping, and the overall function approximates the target function. And now we split this overall approximation into two functions. One is the encoder mapping an input vector to a scalar value, and the other is the composition of the decoder and the target function mapping this scalar value to an output vector. And we approximate these two functions by two networks using existing result that for approximating some function with input dimension plus output dimension is sufficient. So the encoder can be approximated by a network of with dx plus 1, and the composition of the decoder and the target function can be approximated by a network of with dy plus 1. And we further reduces the width for approximating the composition of the decoder and the target function to the maximum over dy and 2. And these approximations result in the network construction of with maximum over dx plus 1 and dy, which achieves the tight minimum width. However, our construction cannot approximate continuous functions in the uniform norm because our construction of ReLU networks cannot uniformly approximate the encoder and the decoder. And as I introduced before, with maximum over dx plus 1 and dy of ReLU networks is probably insufficient for approximating continuous functions in the uniform norm in general. So we prove this by providing a counterexample function from the unit interval to R2 that with 2 ReLU network cannot approximate. To show this insufficiency of with 2, we observe hidden images of with 2 ReLU networks. As ReLU networks alternatively apply affine transformation and ReLU, in the first layer, the unit interval will be embedded as a line segment in 2-dimensional space, and this image will be bent by ReLU. And these alternative application of affine transformation and ReLU will proceed until the output image is generated. And we made two key observations here. First, after applying ReLU, the hidden image must be on the first quadrant. And second, when ReLU bends the hidden image and create new line segments in the image, these new line segments must lie on the axis. And under these observations, we found that hidden images with 2 ReLU networks cannot contain intersecting lines. And this is because when one line segment is created, any line segment cannot cross this line since the hidden image after ReLU must lie on the first quadrant. And we discover a counterexample based on this observation that certain type of images cannot be generated by width-2 Relu networks. So in summary, in the first part of this talk, we found the exact minimum width for the universal approximation and proved that it depends on the target function class and activation functions. And these universal approximation results indicate that narrow networks can also memorize any finite input label pairs. However, these results do not provide the tight required number of parameters for memorizing n input label pairs. So in the second part of this talk, I will introduce our result that narrow networks can memorize n input label pairs using a number of parameters sublinear to n. And to begin with, I will formally define the memorization of input label pairs. We say a function f theta parameterized by theta can memorize some input label pairs if there exists theta such that f theta maps all inputs to their corresponding label. And for memorizing arbitrary n pairs, the sufficiency and the necessity of theta n parameters has been known for various activation functions. And specifically, the necessity result states that for any network with less than n over 2 parameters, there exists a set of n pairs such that the network cannot memorize. And in other words, this result implies that for memorizing not all, but some large class of n pairs, a number of parameters sublinear to n may be sufficient. And this is our motivation, and we aim to characterize this large class of n pairs memorizable using a sublinear number of parameters. And to characterize such class of pairs, we define the delta separateness of inputs. Formally, a set of inputs is delta separated if the maximum distance between inputs is bounded by delta times the minimum distance between inputs. And this means that larger delta implies weaker condition on inputs. And using the delta separateness of inputs, we prove that a Relu network of width 3 and depth n to the 2 over 3 can memorize any delta separated n inputs with arbitrary labels if delta is bounded by 2 to the n to the 2 over 3. In other words, even an extremely narrow network of width 3, a sublinear number of parameters are sufficient for memorizing n input label pairs. And here, our assumption on the delta separateness is mild given the digital nature on data sets, which bounds both the minimum distance and the maximum distance between inputs. For example, any set of 3-channel images of size A times B is 9 plus log AB separated, while this number is often much smaller than 2 to the n to the 2 over 3. And for ImageNet dataset, consisting of 1 million images, is delta separated, where delta is smaller than 17, and it is much smaller than 2 to the n to the 2 over 3. And in the next slide, I will sketch the network construction achieving our result. Our construction is motivated by the network construction for characterizing the VC dimension of Relu networks. We modify this network to implement a Relu network of width 3 and depth square root of m, which can memorize a fixed set of inputs from 1 to m with arbitrary labels. And then we construct a network of width 3 and depth n to the 2 over 3 plus log delta, mapping any delta separated inputs to distinct points in 1, 2, and to the 4 over 3. And concatenating this network and the previous network results in the network which can memorize any delta separated input with arbitrary labels. And as we constrained delta to be bounded by 2 to the n to the 2 over 3 in our result, this construction leads to our memorization result. And let me summarize this talk. In the first part of this talk, I introduced the exact minimum width for the universal approximation and found that it depends on activation functions and a target function class. And in the second part of this talk, I introduced our result on memorization using narrow networks with a sublinear number of parameters, while all existing results require theta n parameters. There are some open problems. As we focused on ReLU networks, the minimum width enabling the universal approximation for other activation function is still unknown. And for the memorization, characterizing the minimum number of parameters for memorizing some given data set is also unknown. And lastly, I'm looking for a postdoc position now, so contact me if you're interested. Thank you.
Thank you for such a lovely talk. We have a few minutes for questions, and I'll start with one. For your first open problem, do you have any conjecture as to whether it's possible to approximate with width less than dx plus 1 with some other activation function?
Actually, I'm conjecturing that the maximum over dx plus 1 and dy is the minimum width for most activation functions. And I'm also conjecturing that for approximating functions in uniform norms, such as this class, the minimum width is strictly greater than maximum over dx plus 1 and dy for other activation functions as well.
Thank you. If there are no more questions, we'll just thank the speaker again and move to the next talk.
Okay, thank you.